Hi everyone, my name is Louisa and today I'm going to be teaching you about how we can find resistance in a complicated circuit. This is the third example video I'm doing on this topic, and today I'm going to try and show you some of the tricks that you might come across and how those tricks can actually be solved pretty simply. Alright, so I've drawn again a fairly complicated looking circuit, and I want to draw your attention to mainly one thing. This used to trip me up when I was first learning circuits myself. You can see here that I've got a path, a part of the circuit that's at a diagonal. And that looks like it's going to be really tricky because you're like, I don't know if it's in series or in parallel. So the very first step when you see a circuit like this is you're going to want to redraw it in a way that's much clearer. So what I'm going to want to do is I'm going to want to move this resistor. I'm just going to draw it up here when I redraw it because it's easier to tell that they're in series and they're next to each other. That's just my preference. You don't have to do that. And I'm going to redraw this angled part so that it's clear the way it works. And when I draw it, you're going to understand how it will work in this circuit. So let me redraw this circuit for you, and hopefully you'll see what I mean. Alright, so this is the exact same circuit. I haven't even simplified it. The only thing I changed was I moved this loop up to this side, the exact same thing. I moved this diagonal, and I made it simply a very easy to understand parallel. I also moved this just down so it was on the same side as this one, so you can just see more easily that we've got two resistors in series here. So now we have the exact same circuit, nothing has been simplified, and we're just going to go ahead and solve it the way we learned how to. Alright, I'm going to erase this top circuit so I have more space. Let's start with the smallest units. I'm going to circle them in red. These two are just in parallel with each other, and there's nothing else interacting with them at that small level. These two are in series, and again, there's nothing else. Neither of them is in parallel with anything else. That's easy to simplify, and then these two are in series. So I'm going to redraw the circuit on top of this and make it a little bit bigger and make those replacements. Before I do that, let me just assign the value R to every resistor. So as I've done in the past, I'm going to go ahead and assume that these resistors are all identical. They all have the same resistance. And so the answer we're going to find is going to be in terms of R. Alright, so now when I draw these values in, I'm going to make some replacements. Since this was two resistors in series, both with value R, the new resistance is going to be 2R. Because when they're in series, you just do R plus R equals R equivalent, and we get R equivalent equals 2R. We're going to do the same thing for this series on the end here. We have two in series, both of resistance R, and we're going to say R plus R equals R equivalent, which is 2R. We're going to replace this with 2R. And now we're going to do this one in parallel. And we know the formula for finding in parallel is just 1 over R plus 1 over R equals 1 over R equivalent. Normally this would be R1 and R2, but since we're only looking at R, the variable R, we can just say R. And so we're going to end up with 2 over R, and R equivalent is going to be R over 2. I'm going to erase this now so I have a little bit more space. And now I'm going to erase the entire bottom circuit since I've redrawn it above. Oh, the only thing I forgot to do is write in the value R for this. Alright. Now we've got this circuit simplified down, so there's no more easy simplifications. There's nothing else where it's just one in series with another, or one in parallel with another. So now what we want to do is start thinking about how we're going to simplify this overall loop, this overall circuit. And we're actually at the point already where we're going to look at the different paths electricity can take. I'm going to draw them in red, green, and yellow. So let's say the red path goes up across this, this part that has no resistor in it, and then it goes back. So that's the red path. The green path goes through this resistor of resistance R, and then it goes all the way around. And then there's the yellow path where it goes through this resistor, goes through this resistor 2R, and then it goes all the way around. So let's consider these to be three different resistors in parallel with one another. I'm going to draw them in a way that should help you understand what I mean. So this is the red resistor that's going to replace the red path. This is the green resistor, it's going to replace the green path, and this is the yellow resistor. Sorry that those resistors look a little bit weird. And now we're just going to have to do some calculating. The resistance for red is just R over 2 plus 2R. So that's going to be pretty easy for us to solve. It's 5R over 2. The resistance for green is going to be the same thing, R over 2 plus 2R plus R. So that's going to be 7R over 2. And the yellow resistor is R over 2 plus 2R plus 2R. And that's going to be 9R over 2. So now we know the resistances. I'm going to erase my work and rewrite these in the corner so they're not in my way, because now we have to solve for them in parallel. And you might be wondering how you can solve for 3 in parallel. The answer is kind of annoying, but pretty simple. You have to solve for 2, solve it down to 1, and then you're going to take, sorry, let me rephrase that. We're going to start with the red and the green. We're going to simplify them down to 1 equivalent resistance, and then we're going to simplify that resistance in the yellow. So you just do it 2 at a time. So let's get started with the red and the green. We have 5R over 2 and 7R over 2. Let me rewrite them. 5R over 2 and 7R over 2. Now they're in parallel, so the way we add them together is going to be a little bit more difficult than if they were in series. We're going to end up with 2 over 5R plus 2 over 7R equals 1 over R equivalent. We're going to have to multiply both sides so that they're easier to add. And we're going to end up with 14 plus 10 over 35R. So it's 24 over 35R. That's 1 over R equivalent. So R equivalent is equal to 35R over 24. Let me rewrite that all so it's a lot easier to keep track of what our values are right now. So the total resistance for this section is 35R over 24, and that means that we can simplify our circuit even further. So we only have 2 resistors to worry about. Sorry. Let's see. Okay, so we're going to do this and do this. This resistor is the one we just solved for, and this one is still the yellow one, which we haven't touched yet. That's 9R over 2. And the gray one we just found is 35R over 24. So now we simply have to solve this the same way we solved the other one. So let's start adding together 1 over R1 plus 1 over R2. We have 2 over 9R plus 24 over 35R equals 1 over R equivalent. Let's make some room. We're going to have to multiply both sides, and it's going to be a little annoying, so I'm going to skip it. I'm going to do it, and then we'll come back. You can do this calculation on your own. It's just multiplication. So when you multiply that out, you get 70 plus 216 over 315R, and that's going to come out to 296 over 315R. And then when we flip it to get the equivalent resistance, we're going to simply get R equivalent equals 315R over 296. And therefore, we've solved the entire circuit. This is the resistance that we would have if we had simplified the entire thing down to a single resistor.